Are you seeing the lecture slide?
Yeah, I can see it.
Okay, thank you so much. Okay, so today the focus is going to be on complex regression, and our attention will be on polynomial regression. So not only that, we're also going to look, going to actually review something on multiple linear regression situation where we also going to where we can consider non-linear effects. So in the outline, okay, I'm going to walk you through polynomial regression. Like I said, there are multiple linear regression with non-linear effect. The work we've been doing, okay, does not have non-linear effects. Okay, but the only non-linear effect that I'm just going to talk about is interaction. Yesterday when we're talking about F test and the partial F test, one of the complicated models we actually worked on yesterday was the one with the interaction. So then I'm also going to walk you through polynomials with several predators. Let's get started. Let's look at the polynomial regression. Okay, we're talking about polynomial. We have second order, we have third order, and so on like that. What I'm trying to show you now is what we call the second order polynomial. So second order polynomial in one variable. What is the variable? X. Okay. Then we have second order polynomial in two variables. And when I say two variables, I'm just talking about having two predators, two explanatory variables. Now, when you take a look at the second one, okay, there is linear effect, there is quadratic effect, then there is interaction effect. You see x1 separately, x2 separately. That's a linear one, right? When you see x1 squared, that's a quadratic effect for x1. Okay? x2 squared, the quadratic effect for x2. x1, x2, that is the interaction effect. Okay? So these two are actually called, okay, they are second order polynomial, except that the first one is a polynomial in one variable, and the second one is a polynomial in two variables. Okay. Now, the order of a polynomial, okay, we normally want it to be as low as possible in statistics. We don't want a situation where we're going to end up fitting higher order polynomials. There's a reason why we want to run away from that. We want to run away from that to avoid what I call overfitting. Overfitting. You see that? We're running away from this guy. Okay? Because when you use higher order polynomials, okay, your model will overfit. Okay? So I'm going to tell you the meaning of all of that. But what I'm for showcasing right now is just to showcase different kinds of polynomial regression that we got. Okay, now going back to the polynomial model in one variable, okay, and we only want to consider the quadratic one. If you take a look at this is a second order polynomial, okay. If I go back, that is the first one, right? Okay, the first one, that guy is the error. Every statistical model has error, okay? So take a look at that. Now, focusing on this guy now, if you want to fit a second order polynomial in one variable, then you need to first understand what is the meaning of each of the components. I want to walk you through this now. You don't just fit a model to data set. You need to first like, what is the meaning? What do they stand for? Of course, you know by now, if beta 2 equal to 0, what happened? If beta 2 equal to 0, you are in simple linear regression. Does that make sense? Okay. Now, what is beta 1? The beta 1 here is a linear effect parameter. Why is it called linear effect? That is the slope when you are talking about the linear aspects. But the beta 2 here is a coefficient of s squared, right? That's a quadratic effect parameter. So which means in a polynomial, in a second order polynomial in one variable, okay, we want to estimate the linear effect parameter. We also want to estimate the quadratic effect parameter. If I generalize to kth order polynomial, okay, do you know that this guy now, kth order polynomial, this is still one variable, okay? We can have a situation where if I stop at 2, that's a quadratic. If I stop at 3, it means it's a cubic. In addition to considering the linear effect parameter, you're also going to consider the quadratic effect parameter. You consider the cubic effect parameter. But when you take a look at the last one, the kth order, that's a general one. We're still focusing on just one variable, except that we are looking at linear effects of that, quadratic effect, the cubic effect, and so on like that. And there's a reason why at times the relationship between variables could actually require us fitting that. But whatever model we fit in statistics, we have a way to evaluate. You remember what we did yesterday? What we did yesterday was comparing models, simple model with a complicated one. We don't want to, because a model is simple, then we're going to choose that for simplicity. No way. We don't want to, because a model is complicated and we want to play to the gallery and just choose it. No way. We have a procedure. Okay. Now take a look at that. Now, and I want to work on the theory of a polynomial model in general. We want to look at the shape. We want to look at the shape of a polynomial model. Now, when you take a look at the first one, that's a linear, right? That's a straight line. Then the numbers of bend in a straight line is 0. There's no bend. There's no any curve. So which means a polynomial of degree 1, the polynomial of degree 1 is linear. There's no bend. The numbers of bend equal to 0. What about polynomial of degree 2? Okay, there's one bend. Polynomial of degree 3, how many bends? 2 bends. If I want to generalize now, I'm going to say there is one less bend than the highest order in the polynomial order, which means if I have a polynomial of degree 1, linear, then we got a 0 bend. Polynomial of degree 2, quadratic, we got 1 bend, and so on like that. Does that make sense to you now? Just to show you, okay, all of that. Now, I want us to go into an example now. We want to fit a polynomial regression model. We don't just fit polynomial regression model. Now, take a look at this example. Very interesting one. I know you guys are familiar with this. How does the numbers of electives taken in an area predict interest in further electives? Let's say, for instance, you are not in statistics. Okay, maybe you are majoring in another course, but you are taking an elective in statistics. Okay, now you now want to see whether taking this elective now, is it going to determine you taking further elective in statistics? And that is why we say, how does the numbers of elective taking, how does the numbers of elective taking in an area, it could be in statistics, okay, predicts your further interest in taking elective in that area? But I want to believe that some students maybe they don't have a wonderful experience by the time they take elective in statistics. Those kind of students we may not come back to take elective in statistics. And there are some maybe who have a very wonderful, experience. They may want to come back. You know what? We now want to investigate this and see. Now I need you to take a look at this. If you see what I'm displaying, this is scatter plot, interest versus electives. Interest here is the response variable, okay? And the electives, the numbers of the electives you've taken in the past from that very area, we basically want to see whether what is going to increase your interest is basically the number, okay? Now, by the time, I told you the other time, when you want to study relationship between two variables before you specify your model, what do you need to do first? You generate a scatter plot. The scatter plot will give you a sense of whether you're going to specify, whether you need to specify linear or non-linear. So take a look at this. You can see a curve, right? Okay. Now, some of you may be noticing the other plot. That's a box plot. The box plot is just contain 5 number summary, minimum, maximum, first quartile, second quartile, and the third quartile. And you can see some points, right? Outside the box plot may be indicating the presence of outliers. Okay. Now, when I generate, take a look at it. Remember the other time, if you want to check for normality, we have assumptions. Okay. The reason, before, the most simplest module in statistics. Can somebody tell me? In terms of relationship, can somebody tell me for extra credit? Okay. By the way, for those of you who have earned extra credits in my class, if you want to use it on the midterm, your midterm result is out, right? If you want to use your extra credit on the midterm, okay, please let me know. And for those of you who are just joining the class, okay, that you've not written your midterm one, please make sure you contact me. I'm going to give you a makeup. I'm flexible, okay? For those of you, whether you miss midterm one, okay, you miss the exam, maybe something happened and you were not able to write the exam, okay, please reach out to me. Or you are just joining the class. Those of you online, can you confirm if you hear that? Those of you
Yeah,
online?
we got it. Thank you.
Okay, thank you so much. Okay, now the most simple. Now, can somebody tell me? I asked a question the other time about what is the simplest model in statistics in terms of when you are fitting relationship. Can somebody tell me? What is the most simplest model? Simplest. Is that one? Which is going to be called what? Intercept model. Send me a message for extra credit. Okay? The most simplest model in statistics is intercept model, followed by simple linear regression. Does that make sense now? Okay, now if I don't want to use simple linear regression, okay, it means assumptions underlying simple linear regression has been violated. That is the reason why we don't want to use it. We need to prove to the world. Why am I not using simple linear regression? This is one of the reasons. The first reason here is I cannot use simple linear regression, when I'm trying to characterize relationship between interest and elective. I can't use simple linear regression because that's a curve. That's not a straight line. That's a violation of linearity. Then, for me to further prove to the world that linear regression cannot be used, then I need to test for normality assumption. And if you take a look at the QQ plot, you take a look at there are several ways to check for normality. You can use the QQ plot. That other guy is what we call a density plot. It's a density plot. You can also use histogram. Okay. So if you take a look at all this, it doesn't look normal. And if you really want to investigate, like want to conduct a test, there's a test that we call Shapiro-Wilkie test. Shapiro-Wilkie test of normality. Okay. So if you want to do, if you want, you need, let's say for instance, uh, MOD, LM. I'm talking. This is the R code. Like if you are fitting a linear regression, Y on S. Okay. Now, if you have MOD, okay, you need to get your residual, which is going to be resid of MOD. And after getting residual, after getting that, you can do Shapiro.test of RES. Okay. When you do Shapiro.test, it's going to return a p-value. The non-hypothesis in the test is normality, is that your residual follow normal distribution. The alternative is violation of normality. Okay. And of course, in the Shapiro-Wilkie test, there's going to be p-value. You compare the p-value with the level of significance alpha 0.05. Okay. If the test, if the p-value is less than 0.05, that's a violation. If the p-value is greater than 0.05, that is not a violation. Okay, so what I'm displaying now is just a graphical means of investigating normality. And of course, different researchers or different students, they may have different interpretations for that. And that is the reason why you can actually conduct a standard test. The standard test, of course, we're actually going to have a uniform position here because you're going to compare the p-value with the level of significance. Okay, take a look at this. Now, what you're seeing now, residual plots. We said something the other time. In order for the linearity assumptions not to be violated, residual plots should not show any pattern. Right now, it's showing pattern, which is indicating violations. Now, let us now do this. Let us ignore all of that. Maybe there's a problem and we're ignoring the problem. That could be dangerous, right? But let us pretend as if there's no problem and take a look at the second output. We run linear regression. Okay. What was the R squared? It's 0.5608. I'm talking about the second one. Do you see this guy here? Okay. For the simple linear, when you look at the first one is when we actually fit quadratic. What was the R squared? The R squared is 0.6726. Okay. So which one has a better fit? The one that has a better fit is a quadratic one. Does that make sense now? That is a quadratic one. And go ahead. Okay, why? It doesn't really matter. The 2p value is so high. If you look at they are more or less zeros. The two of them, raised to power minus 16. Oh, you mean on the quadratic? Yeah, actually, what happened? Our major interest is not on the intercept. Okay, our major interest is on the linear effect and the quadratic effect. Now, when you take a look at the second or the first one, you can see the p-value associated with elective and the p-value associated with elective square is significant. We could have module in statistics, okay, that start from origin. Origin, you know what I mean by origin? That doesn't really matter. Where it start from doesn't really matter. Does that make sense? That's a good question. Now, what I'm trying to display to you now is if I want to characterize relationship between interest and electives, it is better we fit a quadratic model, a nonlinear model, okay, instead of fitting a simple linear regression model. That's what I mean. But that doesn't mean this guy is the best, but it's better than that guy. That's what we mean. Okay, now let us write out the fitted model. Of course, these are the two fitted model, based on the outputs that we got. Okay, using the linear, you can see that. Using the quadratic model, you can see that. And what I'm displaying here is superimposing or having two graph at the same time. If you look at the blue one, that's a straight line, right? If you look at the red one, okay, that is a quadratic one. If you look at the way the if you look at those points, the way they are actually distributed, they follow more closely. It is the quadratic line that follow that pattern, which means the curvature. We call it curvature. Curvature. Give me 1 second. Curvature. Okay, so the linear effect alone cannot capture the curvature in the relationship. And that was why, we're trying to tell the world right now the quadratic actually work. Now, take a look at this. You may want to be tempted, right? Oh, when I use the first order, which is linear, okay, when I use that, and I decide to increase to second order, the R square goes up. You may be tempted again to say, okay, let me continue to increase the order. That is what I want to consider now. Is higher order module necessary? Okay, let me tell you this. I'm going to say this. If I want to fit polynomial, we cannot fit polynomial beyond order 3. Anything after order 3 is not reasonable, except your decision is backed by something other than your data. At times in your feed, you may have a reason to do that. But if it has to do with the data, if the reason is the only reason why you can fit a polynomial other than third order, other than cubic, then the reason for the justification should be beyond your data. Now let's see. How can you test if more complex module is needed? Let's take a look at this. Okay, if you take a look at this now, this is an arrow code, an arrow output for fitting polynomial of order 3. Okay, when I fit polynomial of order 3, what is my R square here? It's 0.6836, right? If you look at the movement, if you look at the increase from what we have initially it was 0.6726, going from 0.6726 to 0.68. That's a marginal increase, which means for this relationship, I don't need cubic. Does that make sense? And another way to show that whether you need cubic or not, we can look at the p-value. Look at the p-value associated with the cubic term. What happened? It's 0.07. That is greater than 0.05. It's not significant. Even without looking at that, when I look at the R square, that was a marginal increase. Okay, because before I can go further, the increase should be significant. And right now, quadratic effect and the linear effect are the one that are significant. Looking at the p-value, does that make sense? But when you look at the cubic effect, that's 0.07. Okay, which get at 0.05, then we don't need cubic. Otherwise, we're wasting our time. Okay. Now, the one I've been explaining, we'll be talking about quadratic effect, cubic effect. What if in a situation where we want to consider multiple regression with non-linear effect? Now, non-linear effect. Now, let's take a look at that. And because of that, I'm going to walk you through another example where we can actually apply non-linear. Describe how to test the nonlinear polynomial, okay, additive effect of mice on 5k times controlling for age. I really, was it not in 2018 or 2019? I participated in marathon with my, you know, with some of our, colleagues or, our neighbors. You know, my children arrive 5 minutes after they arrive. Like they've not seen me. Like, where is daddy? The marathon, you have to go around and stuff like that. Now, take a look at this. You want to look at the effect of, we want to describe additive effect of mice on 5K times, but we want to control for age. Okay, because age is also going to be a factor. Okay, now in doing that, we want to estimate two models, one compact and augmented. The compact one, we only have age centered, and the second one, we're going to add mice and mice squared. Okay, and we're going to test the coefficients of mice squared to see whether we need a quadratic effect of mice. Okay, then we're going to do so many things. But you know what? Let me just take you to results. Let's take a look. Let me talk about the first one. In the first one, I'm only looking at the effect of age on the time. The time you turn in when you run 5,000 miles. Does that make sense? Okay. Now, when you take a look at age is significant when you look at the p-value. The R square was 0.22. Oh my God, that's a poor model. 0.22 multiply that by 100. It means age only able to explain out of 100% variation in time. Age was able to explain only 22.45%. That's a poor one. Okay, even though age is significant. Let me tell you this: the fact that a coefficient is significant in a module does not make that module to be great, because you can look at the R square, so small. When R square is small, it means your unexplained variation is huge. When unexplained variation is huge, you know what it's telling you? There are some very important, relevant variables missing in your model. When you go to the second one, what are we doing now? We added age, we added mice, we also add the quadratic effect of mice. And by the time we run that, oh my God, look at the R squared. Look at the R squared. Now it's 0.7271. That's a good one. And when you look at the significance of the variables you added, they are all significant. Take a look at it. When you look at the p-value, right? Okay. Now, do you know, with this now, we may also want to go further to consider interaction between predators. Okay, but before I'm going to do that, I'm first going to show you this. Look at this. When I talk about second order polynomial model, okay, in two variables with interaction, Now, in this model, now the one we've been considering, we've not been considering interaction. Why do we need interaction in a model? Why is it that the linear effect is not enough, quadratic effect is not enough, why do we need to include interaction? Because a particular explanatory variable, effect of a particular explanatory variable on a response may depend on another explanatory variable. And that's why we may need to include interaction effects. Okay? Now, I'm going to use an example from something that you like. Okay? We're talking about X1, we're using the data on cake. The first variable is temperature. Okay? And we have another variable, okay, apart from temperature. When you actually want to bake a cake, you consider some factors. You basically want to have an optimal cake. Okay? If I continue to increase the temperature, If care is not taken, what will happen to the cake? It's going to burn, right? Okay. And that's why you don't need this. You need a curve. And there's also going to be something like interaction. Now, when you take a look at this now, okay, we look at the linear effects of each variable. We look at the quadratic effect. We also look at the interaction. When you look at the p-value, all of them are significant. When they are all significant, then it means they should be included in the model. Okay? So take a look at that. And even if you look at the multiple r squared, it's 0.9487. That's a very good one. Okay? I think the x1 is going to be temperature and x2 is going to be baking time. Okay? Time and temperature. Okay? And probably the y is the output, like the cake itself. We want a unique cake, right? And you're looking at the effect of the baking time and the temperature. And of course, we can't just use linear here. There's going to be a curve. And not only that, the baking time, effect of baking time on temperature may depend on, effect of baking time on the output may depend on temperature. That's why we need interaction effect. And because it is significant now, look at the p-value, 0.004654 indicates that is true. That temperature, effect of temperature, okay, on the output, on the response, actually depend on the baking time. When interaction is significant, you know what that means? When interaction is significant, it means, the variable you are using, your independent variable, are not consistent. Okay? Because the effect of it, of one of that on the response, depend on the other one. If I want to write a fitted model based on this, when I want to write a fitted model, you're going to make use of the X image. Go ahead. Oh, okay. I'm still going to talk about all of that. When you are fitting polynomial, okay, when you fit polynomial directly with your data set, that means the raw is true. Okay. At times, if you want it to make more sense, we basically are going to standardize the variable before we fit. Okay, I'm still gonna that is gonna be for another class, because you know why? With all this, there's gonna be a violations of multicollinearity. In multiple linear regression, we don't expect independent variable to correlate. But in this case, of course, they will correlate. You know why? X1 square depend on x1. Does that make sense? S2 square depend on s2. And x1, s2 depend on s1 and s2. In that situation, what happens? There's a problem of multicollinearity. Multicollinearity. Multicollinearity is when independent variables have relationship. They shouldn't have any relationship. So in that situation, okay, one of the intervention is to standardize. Okay, we're still coming back, we're still coming into all of that. But what I'm just teaching now is just like, okay, let's look at the polynomial regression, fitting that with the raw data set. Okay, this is the mean equation. That is the mean equation. Okay, using the model, it's like a fitted regression model, right? So take a look at that. It's a fitted regression model. Okay, this is the output again. Okay, the output that we got. Okay, now let me tell you this. How, after getting, if you take a look at this, right? What this is going to tell you is the role played by variables in this model. But does that tell you the optimal values of baking time and the optimal temperature that you're going to use for you to have a good cake, a unique cake? It doesn't tell us. The only thing this guy is telling us now is, okay, you know what? Baking time has relationship to the output, the temperature also have. But if I now want to figure out, if I want to estimate the optima, well, what we're going to be the optimal baking time, I'm actually going to set what is going to be the optimal, temperature that I'm actually going to set. And when I figure out a value of optimally, I need a standard error for that because I may want to test hypothesis about that. So that was why you say estimate the optimal, optimal X1 S2 combination and the standard error. How am I going to do that? Oh my God, I'm actually going to use the knowledge of calculus. When you have an equation, you have a mean equation, okay, and you are looking at a unique baking time and unique temperature, what are you going to do? You're going to differentiate with respect to x1. You're also going to differentiate with respect to x2. What are you differentiating? You are differentiating. It's just like we want to differentiate this guy. This is a model, right? That we got, right? Okay, differentiate. Before you can get the optima, you need to first investigate whether x1 x2 has a significant contribution, we've already established. And what we want to do now is just to go on and we want to get the optima. Okay, you do the derivative, respect to x1 respect to x2. That is what you got. And you're going to set it to 0, right? Then you obtain x1 and x2 star. The x1 star, the x2 star is basically the optima. And what do they depend on? They depends on the regression parameters. Look at that. B2, B5, all of that, they are already in the table here. They are already in the output. Okay. The beta naught, this intercept is the beta naught. The beta naught is that first one in the estimate. The beta 1, the beta 2, the beta 3, the beta 4, the beta 5. Does that make sense? You already have them. Okay. All what you just need to do is to plug in them. Okay. You want to plug them in. Okay. Okay. But you know what? That is what I coded here. Do you see that? X dot mass and x2 dot mass. Do you see what I coded? So in R, if you want to get the optima, instead of you to just go the way we went the other time, okay, when you write data method into M1, all of that is basically going to give you the estimate for the two as well as the standard error. You follow that code. You're going to have the estimate. So that estimate now, it means, okay, when I have a unique baking time and I have a unique bell temperature, then I'm also going to have a standard error associated with them. Does that make sense? Okay, another thing that I want to talk about today, another example. I want to look at effect of oxygen on IgG. There's something that we call hemoglobin, right? And when we're looking at the relationship, when you generate a scatter plot, does that look like a straight line? No way, right? That's not a straight line, right? Okay, that is looking like a curve, right? Now then you now need to what? You need to fit a polynomial. Okay, you see that we fitted the polynomial. That's exactly what we got. Okay, that is the model when you fit the polynomial. Now let's show the output. Okay, now when you fit the polynomial, okay, when you look at the here, okay, I need you to pay attention to something. Do you see VIF? VIF? VIF is what we call variance inflation factor. Variance inflation factor. Okay? VIF means variance inflation factor. Now, we normally, if you want to get a VIF after running your model, you remember the other time, like, because in a multiple linear regression, how do I check if there's a problem of multicollinearity? Okay, after running your module, your module is LM Y on this, right? Now, if I want to get my the VI, I'm just going to do VIF into MOD. Okay, and that will do the return all this. What is a threshold? When a coefficient has a VIF greater than 5, then it's problematic. There's a problem. Now, what do you see here? Oxygen and oxygen square. I told you the other time. Of course, oxygen square depend on oxygen, right? X square depend on X. Now look at the VIF for oxygen and oxygen square, 99.94, which is far greater than 5. I told you, VIF greater than 5 means there is multicollinearity. Does that make sense? One of the assumptions of multiple linear regression is there must not be multicollinearity. In addition to linearity assumption, normality, constant variance, independence, absence of outlier, we also have additional assumption that's no multicollinearity. Now, situation where a predictor has a VIF greater than 5, okay, then you actually there's a problem of multicollinearity. Now, it means, generally speaking, the polynomial regression we've been celebrating, okay, even though it solved a problem, it created a new problem. And which problem did it create? Multicollinearity problem. And when a module has a multicollinearity problem, you cannot trust the module. Okay, this is VIF, is greater than that. Now, what am I going to do to correct that? That was the reason why you saw raw the other time. When you use the raw data, okay, there's going to be problem because there's going to be multicollinearity issue. So what we're going to do is, let us first, do what I call discrete. Let's generate discrete statistics. You see the minimum, the mean, right? Okay. Now, you see the maximum, right? And the VIF of oxygen and oxygen square is greater than 5. Now, what I'm going to do now is I'm now going to centered. Okay? If I'm going to center, take a look at, but before I centered, what is the meaning of B0? The intercept in polynomial, predicted response. Okay, when s equal the sample mean, if I've centered without centering, okay, it's going to be intercept, right? But if after centering, because why am I centering? I'm centering because I want to go away from multicollinearity. So one of the way to escape multicollinearity in a polynomial regression is by centering, which is standardizing. Okay, now let me just show you, because of my time, let me show you after now let me just show you what we mean by centering. You're going to see now what we mean by centering. Now let's say we have y equal beta naught plus beta 1x plus beta 2x squared. This is a polynomial, right? By centering, okay, I'm going to do, I need a new x star, which is x minus x bar. Okay, x minus x bar. So my new module now is going to be this. Does that make sense? That's a centered one. By centering, it means I'm subtracting the mean of it from the respective variable. That means I'm standardizing. So when I do that, then what is going to happen now? Let's look at the VIF after centering. What do you see? Look at the VIF. Oh, VIF is friendly, 1.05 now. This result is after it has been centered. Does that make sense? Okay. Now, that is the one we can trust. Now, there's something I want you to pay attention to. Look at the estimate for intercept here, 1632.3 after centering. And I'm going to show you when we have not centered, what is the same value, okay? Without centering, negative 1464. They are not going to be the same. Does that make sense? Okay. Now, if you take a look at after centering now, we have that. Okay. Now, this is our module now. This one, the one that we got that we get here, 1632, 34, whatever, those ones we did not use the raw data. We actually center, like we standardize. One of the way to break out of multicollinearity is to standardize, which is what we've done. But interpretation is no longer going to be the same. Okay, how is it going to be? I need you to pay attention now. How is it going to be? The interpretation, the intercept is going to be talking about take a look at this, the estimated coefficient, okay, which is that tell us that a male whose maximum oxygen uptake is 50.64 is predicted to have that. Where is the 50.64? Okay, the 50.64 is going to be the mean. Let me take you back. Do you see that? Do you see 50.64? Does that make sense? That is going to be the mean of the oxygen. The one you are using, see, the one you that is what you are subtracting from all of that. Does that make sense? So that is what that is telling you. Now, now how do you now interpret the B1? Okay, okay. Tell us that when an individual maximum oxygen uptake is near 50.64, near 50, that is nearing the average. Okay, near 50, we can expect individual immunoglobulin to increase by 34 for every 1 ml per kg increase in maximum oxygen uptake. Take a look at that. Then how do we interpret this guy? You know, the quadratic term, we don't need it. We don't need it. Okay, we don't need it. We don't need to interpret quadratic term. But there's something I'm going to show you. If you really want to, take a look at it. The quadratic time is just going to tell us this. Is it concave down or concave up? You know, quadratic. Okay, take a look at that. It's only going to tell us the direction of the curve. You see that now? So if I want to interpret my coefficient in the polynomial regression, okay, the intercept is going to be the estimated coefficient B0 is the predicted response Y when the predictor S equal the sample mean. Sample mean of what? Of the predicted values. Does that make sense? Of the predictor values. Predictor here is oxygen. Okay. Now, the estimated coefficient B1 is the estimated slope of the target line had the predictor mean, and often it is similar to the estimated slope in the simple linear regression. Then what about the B2? The quadratic one is just going to show us the direction of the curve. Okay. Now, by the direction of the curve, if B2 is less than 0, it's going to say it's concave down. If it is greater than 0, then it's concave up. That's all. So, and in this situation now, where it is greater, we're told that it's greater than 0 is going to be concave up. Okay, positive. Okay, there's going to be concave down here because it's negative. Does that make sense? Is there any questions before I go? Is there any question? Okay, the takeaway. Okay, go ahead. Or you mean one slide or one more? Oh, the conclusion, right? Yeah, yeah. So which means after you've standardized, okay, your focus is going to be on nearing the mean. The mean of what? The mean of the predictor. The mean of the explanatory variable. Okay. So, applying this, there's not going to be multicollinearity. There's not going to be violation of multicollinearity because we've already tested that. You see, the VIF is 1.05. Initially, it was higher than that. With this, we're safe. But interpretation is going to change. Okay, any question before I go today? Okay, in the absence of question, make sure you stay safe and have a lovely day. Bye for now, everyone.
Thank you.
You welcome.
Thank you.
You welcome. See you tomorrow.